So we're in our kinetics unit, and we have now learned how to make our rate, which is our formula that we are going to use to determine rate for every reaction. Now, our K, which is part of our equation, takes into account the energy of collisions and the orientation of collisions, and our concentration here is in brackets, that's in molarity. So remember that in order for a reaction to happen, these collisions have to happen with enough energy in the right orientation. And the more particles I put in, or the higher the concentration, the faster I can make that rate go, depending on this order. And so far they have told you what the order is, but now we're going to figure out how to determine it experimentally. And we're going to do this using initial rates. So first let's look at this graph. This is how concentration changes over time. And here I have A plus B is going to my product C. So basically these two are going to react, and they are going to go down to zero concentration if it's a non-reversible reaction. And as they disappear, my concentration of my product is going to up here. And this concentration and the initial rate, how fast do these disappear, is how we are going to determine that order. Okay, so first let's take a look at what these orders do and how this concentration affects the speed of our reaction. So for this example, we are going to just use this rate law. Rate equals K times the concentration of A. We're just going to say it's A to B. Okay, and we're going to try and figure out what this order tells us. And for all of these examples, my K is going to equal 1. My rate constant, which is lowercase k, okay, it's not a capital K. Capital K is for equilibrium. Lowercase k is going to equal 1, so we can just kind of drop it out. So if my order for that reactant is 0, what happens? Well, if I put in 1 molarity of A, my rate is going to be 1 molar, okay? Now let's say that I double that rate to 2. Well, my order is 0 here, so anything to the 0 order is 1. And so my rate is still 1 molarity per second. So changing my concentration does not affect the rate with 0 order. Let's look at what happens if A is to the first order. So here I put in my 1 molarity, and my K is 1. So 1 times 1, I get a rate of 1 meter per second. Let's double that concentration to a molarity of 2. Okay, so 1 times 2 to the power 1 gives me a rate of 2 molarity per second. So for first order, I doubled my concentration 1 to 2, and my rate also doubled 1 to 2. So in a first order reaction, if you double something and it doubles, it is going to be first order. Okay, so what about second order? Well, second order is raised to the power of 2. So I'm going to start with 1 molarity. My K is 1, so my rate is going to equal 1 molarity per second. What if I doubled that to 2? Well, 2 times 2 is 4 times 1 is 4 molarity per second. So for the second order, if I double the concentration, I quadruple the rate. Why? Because it was to the square. If I tripled it, it would go 9 times, because 3 to the square is 9 times. So there's some math involved here that you guys are going to disregard at this level. You're just going to look at your rates, and if I double my concentration and the rate doubles, it's first order. If I double my concentration and the rate quadruples, it's going to be second order. If I change that concentration and nothing happens, it does not affect the rate, which is why when it is to the 0 order, we can just say rate equals K, because that concentration does not affect it at all. Okay? So here's the kind of problems you're going to have. You need to find your rate law from data. Okay, so from the data we're going to determine these orders, right? I can write my rate law right from here, but it's generic. I need to figure out what these orders are, and then using your data, you're going to plug it back in and you're going to solve for K. So let's take a look at this. First of all, as I showed you on the graph, we're going to do initial rates from initial concentration. So we have concentration of A and B. And I have a bunch of concentrations of A here, but you can see 2 are held constant. And for my B, 2 are held constant here. So if I want to find what happens when A is doubled, I have to look at where B is held constant, because I can only change one thing at a time to see how it affects it. So here, my rate is doubled, B doesn't change at all, and 1.1 times 10 to the second to 2.2 times 10 to the second, my rate was doubled, okay? Concentration doubled, my rate is doubled. So, trial 1 and 2, B was held constant, I doubled A, so I doubled my rate, which means my A is first order. So then we need to see what happens when B is doubled, and I need to look at trials 2 and 3 here because my A needs to be held constant when I look at what happens when I change B. So B right here is doubled, and my rate goes from 2.2 to 8.8. That's times 4. So when I doubled my B, my rate quadrupled, which means B is in second order. So then I can write my rate law. Rate equals A to the first order, B to the second order. And then I'm going to use trial 1. I'm going to use these numbers because now I have my equation. If I plug in my rate and my concentration of A and B, I can solve for K. So if I pick one of these trials, you can't mix and match. You have to pick one. There's my concentration of A, there's my concentration of B, and there's my rate. And that's what I'm going to use to plug in this equation and solve for K. So here is my rate law. I figured out my orders. My concentration of A is 1.0, my concentration of B is 1.0, and my rate was 1.1 times 10 to the second. Now we need to look at K units. If you want to ignore this part, go ahead. It's just an extra credit for IU. But K has different units based on these orders. So remember, brackets are molarity, and this is molarity squared. So I have 1 molarity times 1 molarity squared. That's 1 molarity to the third equals this rate, okay? Then I need to divide by 1 molarity squared on both sides to get K alone. So my K is going to equal 1.1 times 10 squared. Now notice my rate is molarity per second, and I divided it by molarity cubed, right? Molarity times molarity twice, divided it by molarity cubed. So 1 molarity goes away, and that becomes molarity squared. And seconds is on the bottom. So I have 1.1 times 10 to the power of 2. Molarity to the minus 2, seconds to the minus 1. And remember, that means 1.1 times 10 to the power of 2 divided by molarity squared seconds, because that's what the minus 1 means.